The stress life method is the original approach used for understanding and quantifying metal fatigue. It was a standard fatigue design method for well over 100 years, and it's still widely used in design today. While this method does not work for low cycle fatigue, less than 1,000 cycles where there's a lot of plastic deformation, it is the ideal method when materials have much more than 1,000 cycles to failure, when parts are primarily subject to elastic loading, or under conditions where parts might have infinite life, where they're cycling at a load level so low that there's an infinite number of cycles to failure. Now, the standard stress life fatigue test is conducted under what we call completely or fully reversed conditions. Now, to understand that, let's look at a diagram of the stress versus time plot for a fatigue cycle. Completely or fully reversed means that during a fatigue cycle, we go through equal parts tension and compression, meaning the magnitude of the maximum minimum stresses are equal and their signs or senses are inverse. One is in tension and another is in compression. Under these conditions, the mean stress or the average stress of a cycle is equal to 0. And the range of cycling is the max minus the min, right? Now, the key parameter that we use in the stress life curve is the stress amplitude, which is the average, not the average, but the maximum plus the minimum stress divided by 2. So it's half of the range of our cycle. Now, how do we get a completely or fully reversed test? How do we perform that test? Well, a fatigue test typically can take a very long time to complete. And if we're just going tension, compression in an axial way, it can take a very long time. How quickly can we cycle in tension and compression? Kind of limited in an axial way. So one of the first and most widely used machines to do fatigue testing is the Wöhler experiments, also called the R.R. Moore test machine for high-speed rotating beam bending of samples. Now in this test, what do? In this test, we specially machine a sample and polish it so its surface is pristine. And then we subject it to a pure bending mode. So we get it bending, usually by hanging weights at a certain point across its body. And then we spin up that sample at a very, very high RPM. And this leads to the outer surface as it spins going from pure tension to a pure compression. And we're actually able to get a beautiful sine wave everywhere on the surface as this thing spins up. And by being able to spin it up to a very high RPM rotation per minute, we can generate billions or trillions of cycles into a sample in a very short period of time. Now, the scientist who kind of originally developed this method, August Wöhler, was active from 1819 to 1914, and he is the OG who actually created the stress life plot, the curve, originally called the Wöhler curve. He invented the rotating beam test machine, and with this machine, he was able to spin up samples and identify the endurance limit, which is the stress amplitude below which materials appear to have infinite life, meaning they can just cycle forever, right? And he was also a German railway engineer at that time with the Industrial Revolution. There was a lot of locomotive work going on. There was a lot of fatigue type failures. And so his experiments helped kind of expose the concept of stress amplitude or fatigue cycling to failure, right? Now, some key things that we can look into. There's a supplemental video that actually goes into the modern Wöhler machine that shows an actual example of the current machines that people use. This test is still very much alive. Now, what is the outcomes of running one of these tests? Well, the outcome is a stress life curve, which relates the stress amplitude, sigma A, to the cycles to failure, NF. Each data point in our stress life curve represents a separate experiment. So a separate sample is loaded in the machine, spun up until at a certain stress amplitude to give us a certain cycles to failure. So in order to create this SN curve for any one material, many experiments, hundreds potentially, need to be performed so we can characterize a material's behavior and identify the endurance limit below which a material appears to have infinite life.